Yesterday we graphed rational functions, specifically in inverse relations. And today we're going to talk, an inverse relation is a type of rational function, just like this one. This would be an inverse relationship. And so when you graphed it, you would get the two curves right there. So when we have this, we always end up with a variable. Usually your input or your x variable is somewhere in the denominator of a fraction. Well, when we have fractions in a function, what happens is we have values that we cannot use. Okay, excluded values. The reason we have values that we cannot use is because we already know if we are dividing, we cannot divide by 0. We cannot have a 0 in our denominator. So for whatever values for that variable that would give us 0 in the denominator, that is an excluded value, meaning our domain is going to be everything except that specific value. Okay, so how we're going to spend the first part of this lesson determining what values are excluded. So, and all that means is we look solely at our denominator and we have to say, okay, well, if that denominator cannot be 0, if 3 times x cannot be 0, now in the book they're going to set it equal to 0. But I like to use the can't equal sign because that's really what we're finding. We are finding what x cannot be. And if I divide by 3, it doesn't really matter because it's 0. So for this one, the domain would be x is all real numbers except for 0 because it can't be 0. Look at this next one. Now that was a product. This is a binomial. So we take this binomial, x minus 2 cannot equal 0. Well, if x minus 2 cannot be 0, well then x cannot be a positive 2 because a positive 2 minus 2 would give us 0. So your domain is all real numbers except 2. All right? Keep going. It continues. Like this is still a binomial over here. It's just a little more complex. So we've got 2x plus 10 cannot give us 0, which means 2x cannot give us negative 10 when I subtract 10, and when I divide by 2x cannot be negative 5. So again, on this domain is all real numbers except negative 5. Now these numbers are going to come back up in a little bit, and we'll see why they're important, why these values become super, super important in our next lesson. Well, hold on. No, in this lesson, just in a little bit. Okay, so here's a real world problem with the same thing. So let's say Samantha's jogging. She's jogging an 8-mile trail. Her average rate in miles per hour, y, is given by this. So her rate is 8 miles divided by, obviously, how many hours? So, because that's going to give us miles per hour. So, if we're putting numbers in, what kind of numbers are we going to put in for x? Well, positive numbers, because she's running for some amount of time. Time is not going to be negative. So I'm not going to put in 0 because it obviously took her some amount of time to run 8 miles. But let's just say it was 1 hour. Why do I pick 1? Well, because I can divide 8 by 1, right? 8 divided by 1 is 8. So her miles per hour would be 8 miles per hour. Makes sense. Okay. 8 is divisible by 2 also. So if I put 2 hours in there, she's going 8 divided by 2, 4 miles an hour. And if I put 4 in there, 8 divided by 4 would be 2 miles per hour. So now she's walking. And last but not least, I can divide 8 by 8. And that gives me 8 divided by 8 is 1, which means 1 mile per hour. So obviously she's not jogging. If she's only going 1 mile per hour, she's basically crawling. But it just doesn't change. So let's plot these. 1 hour gives me 8, speed of 8. 2 hours gives me a speed of 4. And then 4 hours is 2, and 1 hour is 8. So again, this is an inverse relation because it has to equal 8. My product has to be 8. I don't need to do the negatives because I'm talking about hours and speed, and that really, but if I did, it would be down here, right? It would be down here looking the same. So graph where x is total, graph this function. There you go. So that's a real life application. Now, I'm not sure how real life, because if she's running over 8 miles per hour, that is booking it for 8 hours, for 8 miles. But okay, so that is a graph. Let's turn it over and let's talk about this. So why are these why are these values that we have to exclude important? Because there's something called asymptotes. Okay, yep, that sounds funny, asymptotes. So what that means, it's a vertical line that it gets close to, but it can never be equal to. Now, up until prior to this, it was always 0. It couldn't be 0. That's not always the case. So if we look back here, in this one, it was, in that first example, it was 0. But in the second one, it was 2. So x can't be 2. It can be anything prior to 2 or above 2, but it can't be 2. And same thing down here. It can't be -5. So if x can't equal that number, what that means is it's a vertical asymptote. It's a vertical line that's going to cut our graph. So check that out. Now, there's also a horizontal asymptote. So if we add a number to the end of our equation, so this will approach a number, and then that approaches a number. So your horizontal asymptote will be y equals c, whatever number we are adding on to the end. So that's our vertical or our horizontal asymptote. So let's do a couple examples like this, shall we? Down here. Now I'm going to get out some highlighters. I'm going to create my asymptotes with highlighters so that you understand that those are places that we cannot be. All right, so here's our overall equation. So whatever this number is our x asymptote, our vertical one, and this will be our horizontal one. So let's look at our equation. Pretty simple in this equation. The only thing in my denominator is x. So the only thing that x cannot be is 0. So our vertical asymptote is 0. And take a look at that. I'm just going to, on my graph, I'm going to put a highlighted right there. Our lines or our curves will never actually touch x equals 0. Now, this one right here is our horizontal asymptote, which means on the y-axis, we've got a horizontal line. It will never equal that. So now when we make tables, I'm going to make a table based on my function. So x and y. Now here's my equation. Y equals 3 over x plus 2. Don't use hideous numbers, right? Use good numbers. The first number I'm going to put in there for y, honestly, is going to be 3. Why 3? Well, because 3 divided by 3 is going to be 1. And then 1 plus 2 is 3. So if I put 3 in there, 3 divided by 3 is 1 plus 2 is 3. Now, I'm not going to put 2 because that's going to be kind of ugly, but if I put 1 in there, that also works good because 3 divided by 1 is 3, plus 2 is 5. Okay, what if I put in, let's see, what else? Let's do 1/2. What is 3 divided by 1/2? 6, and plus 2 would give me 8. Right? How about 1/4? 3 divided by 1/4 would be, 3 would be 12. 12 plus 2 would be 14. So let's plot a couple of those. Now this one's obviously, actually these two aren't going to fit on there. So maybe let's put in the 2. If I put in the 2, 3 divided by 2 is 1.5, plus 2 would be 3.5. Okay. So what if I put in 4? I want to put in 4. 3 divided by 4 is 3/4. That would be 2 3/4. If I put in, say, 6, that would be 3 divided by 6 is 1/2, and plus 2 would be 2 1/2. So ignore these two. I'm not sure why I picked those two. Let's go here. 3, 3, 3, 3. 1, 5, 4 and 2 2/3. 6 would be 2 1/2. So do you see how, oops, up here I have my arch, my curve that's going to continuously get closer. Now I'm going to pick numbers over here. So let's go X and Y. Let's go ahead and do some negative numbers, right? Some negative below my vertical asymptote. So let's go easy, -1. -1 is going to be -3 plus 2, which would be -1. So -1, -1. Ooh. All right, well, let's go -3. I'm going to save some room. -3 divided by -3 is -1, plus 2 is 1. So there's -3, 1. Let's do, I know this is ugly, but let's do -1/2. Okay, 3 divided by -1/2 is -6 plus 2 is -4. So right there. And just for good measure, let's go -4. 3 divided by -4 is -3/4 plus 2 is 1 1/4. So right here. So you can tell, or hopefully you can tell, this is where my line is going to end up. All right, picking X values strategically, making sure we've got something that's going to make sense in the end. All right, let's try another one. Oops, on the next page. On the next page, here's another example. Now this one's got a binomial in the denominator. So remember, X minus 1 cannot equal 0, which means X can't be 1. Well, that means that's my vertical asymptote. My horizontal asymptote is whatever we're adding to it. Well, we're not adding to anything, so it's 0. So vertical, we're going to be right here, and horizontal is actually going to be right on this axis, right there. Now when I pick my values to put in there, I'm going to pick values, I'm going to do a better job than I did last time, and I'm going to pick values according to my vertical asymptote. So when I'm plugging in numbers for X, guess what? I'm going to go ahead and plug in, I know this looks goofy, but I'm going to go 1 1/2. Okay, so 1 1/2 minus 1, which is 2 divided by 1/2, which is going to give me 4. So 1 1/2 gives me 4. Well, let's keep it easy. Let's go 2. So 2 minus 1 is 2 over 1, or 2. All right, let's keep it there, 3. So 2 over 3 minus 1 is 2 over 2, or 1. Let's go 4. 4 minus 1 is 2/3. Just for good measure, what if I put 5 in there? 5 minus 1 is 4, and that's going to be 1/2. And I'm going to stop right there, because hopefully you can identify that curve. All right, let's try the other one. Now, I started at 1. I'm going to start here, maybe 1/2. If I put 1/2 in there. So I've got 2. 1/2 minus 1 gives me 2 over -1/2. That's -4. So at 1/2, we are down here at -4. So how about 0? That's an easy one. I know that you're thinking, oh, we can't do 0 in the denominator. You're right, but it's 0 minus 1, which would be 2 over -1, which is -2. How about 1? Oh, just kidding. How about -1? Because 1 would not have worked. Okay, so -1 minus 1 would be -2. So 2 over -2 would be -1. And -2, which would be Negative 2 minus 1, which would be 2 over negative 3, or negative 2/3. All right, I think we see what's happening here, so let's do this. 1/2 was negative 4. Oops, that should be here, not there. I apologize. 0 is negative 2. Negative 1 is negative 1. And negative 2 is 2/3. Negative 2/3. So here we go. There you have it. Oops, made a better arrow over there. So we will be graphing some functions again today. Graphing a little bit, stating the values, the excluded values, and graphing them. Just so far, we know what a linear function makes a line, but here's the 4 types of nonlinear functions that we have specifically worked with. Way back, the quadratic function, which would be a parabola, right? Then we went to exponential functions, where our variables are exponent, and that gives us one curve, and then the square root, which gives us the funky one, up, down, left, right, and last but not least, our rational function. Now we have 2 separate curves. Those are the 3 nonlinear functions that we've gone over so far. All right, so your assignment is on the back of your paper in orange. You'll see it there. For 12 through 19, you're just giving the excluded values, but you will have to graph 6, 22 through 27. All right, 22 through 27, identify the asymptotes, so you're going to have to tell me x equals this and y equals this, and then you graph them. Pick variables or pick numbers that make it easy on you, all right, that you can use. Stay small, and it'll be okay. All right, so if you have any questions, come and see me. Good luck.